Alright, hello everybody. So today we're going to be talking about, or at least in this chapter, we're going to be talking about infinite sequences and series. So the first thing we need to clarify here is sequences versus series. Okay. So I'll say here, in English, these words mean the same thing. Okay, so in English, these two words mean the same thing. So I'll say here, a number of things or events coming one after the other in some given order. Right, so just like a sequence of events or a series of events. That's kind of how we use that language. And I'll say here in the dictionary, so the dictionary uses each word to define the other. Right, so via just the English dictionary, these two words are the same thing, sequence and series. But here in math, we're going to say that they're actually different things. So in math, what we care about, so I'll say here that sequences and series do not mean the same thing. Right. So I'll say here a sequence. So let's talk about what a sequence means. So a sequence is a list of numbers in some order. Right, so an example, I'll say here, an example of a sequence is, we just pick some list of numbers. So I'll say here a sequence is, let's say we have 1/2, 1/4, 1/8, 1/16, and so on. Right, so this is just an infinite sequence of numbers. Notice what I'm doing every time is just dividing the number by 2. Right, so just any list of numbers like this we'd call a sequence. So that's what we mean by sequence. But let's say what we mean by series. So a series is a sum of a list of numbers. Right. So let's look at an example of a series. Example of a series. So one example is going to be, let's say we had 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and so on. Right? So here the difference is, and this is a very important difference, right? This is key to the whole chapter. The difference is a sequence is just a list of numbers, whereas a series is a list of numbers that we're adding together. So this is actually just a number, a series, right? So if you add a bunch of numbers together, you either get a number or you get infinity. And a sequence is just a list of numbers, right? So a sequence is a potentially infinite list of numbers. A series is a potentially infinite sum of numbers. So that's the difference there. So let's say here some sequences in series. Right, so I'm just going to write down some examples here. So the first one is called the Fibonacci sequence. So the Fibonacci sequence is 0, 1, and every time we just add the previous two numbers. So 0 plus 1, that's 1. 1 plus 1, that's 2. 2 plus 1, that's 3. 2 plus 3, that's 5. 3 plus 5, that's 8. 8 plus 5, that's going to be 13. 13 plus 8, that's 21. And you just keep going, right? So that's how we define the Fibonacci sequence. It's just this infinite list of numbers where you're just adding the previous two numbers together to get the next number. Okay, so that's a sequence because it's just a list of numbers. And so I'll say here, let's say if we had, so just another example here. Let's look at another example is, let's say we have 1 minus a third plus a fifth minus a seventh plus a ninth minus and so on. Right, so here we're just adding together a bunch of things, right? Some of the numbers are negative, but we're just adding together a bunch of things. So we're just adding and subtracting and so on. We call this a series. And it turns out what we get here is actually going to be pi over 4. Right, so the Fibonacci sequence actually occurs in many different areas that you wouldn't expect. And another cool example here is that if you just add together this weird list of numbers, just adding together these fractions with all the odd denominators, then you actually get pi over 4. Another interesting example of a series is, let's say you have 1 plus 1/4 plus 1/9. You can kind of see what I'm doing right here. I'm dividing by each number squared. So this is 2 squared, this is 3 squared. Here I should divide by 4 squared, so I'm going to divide by 16. Then I'm going to divide by 5 squared, which is 25, and so on. Right? So if I just have that infinite series, then if we just add all of these things together, it turns out what we get is pi squared over 6. So that's another example of a series. And the last example we'll talk about here is called, I'm actually not sure how to pronounce this, Collat's, probably, conjecture. So what this is going to say is start with any number. If the number is even, divide it by 2. And if the number is odd, multiply it by 3 and add 1, right? So the conjecture is if you just start with any number and you do these operations until you can't anymore, the conjecture is that eventually you just always get to 1. So let's check this. Alright, so let's just start with a random number. I'm going to pick 5. And we're just going to follow this procedure that it says here. Right, this is a sequence because we're just getting a sequence of numbers. So I'm starting with 5. If it's odd, I need to multiply by 3 and add 1. So 3 times 5 is 15, add 1, you get 16. So that's an even number, so it says we need to divide it by 2. So we're going to get 8. And that's also an even number. So we're going to get that divided by 2, which is going to be 4. And that divided by 2 again, which is 2. And that divided by 2 again, which is 1. Right, so as soon as you get to an even number, you can see, well, you're going to eventually get back to 1, because you're just going to keep dividing by 2. And then you can see, well, what happens after we get to 1? So 1 is odd, we multiply it by 3 and add 1. So we get 4 divided by 2, divided by 2. And then this is just going to keep repeating itself, right? We can just keep doing this. And we're just going to keep bouncing back and forth between 1, 4, 2, and 1, right? Okay, so we see it works for 5. Let's just try another number. Let's say we try 6. So that's even, so we can divide it by 2. So 3. That's odd, so we can go ahead and multiply it by 3 and add 1. So we get 10. That's going to be even, so we divide it by 2 to get 5. And then 5, we can say that's odd, so we'll multiply it by 3 and add 1, so we get 16. We already saw what happens whenever we get 16. We divide it by 2, and since this is a power of 2, we can just keep dividing it by 2. So we get 4, 2, 1, and then again we get 4, 2, 1, and so on. Right, this just keeps repeating itself. So the conjecture is just that whenever you start with a number and you do these operations, you always get back to 1. So that's just kind of an interesting example of a series, right? The series that you get by doing this procedure, it turns out you always get back to 1. Or sorry, did I say series? I meant to say sequence. That's what I meant to say. This is a sequence because it's a list of numbers, right? So this list of numbers, this list of numbers, these are just both interesting sequences. So these are sequences, series, this is another sequence. Okay. But today, actually, our main focus is on sequences. So the first section of this chapter is just going to be on sequences. Or actually, I'll just put 2 on the board here. So today we're going to talk about just sequences. So just lists of numbers. Okay. So given a sequence, let's say our sequence is A1, A2, A3. You keep going until you get to, let's say, AN, then you just keep going, right? So this is an infinite sequence. It just goes on forever, just an infinite list of numbers. And I'm just giving the numbers, the entries names, right? So this is entry 1, this is entry 2, and so on. Okay. And I'll say here, we call A1 the first term. And A2, you can say, well, that's going to be the second term. And let's say you have AN, well, that's the nth term. Right. So just given the sequence, we just say that each entry is, we call it a term, right? So it's the first term, second term, and we've got the nth term there. Okay, and I'll say for this section here, we'll deal exclusively with infinite sequences. So each term AN has a successor an plus 1, right? So the n plus 1th entry, which would be right after the nth entry. This is an. Okay. And a predecessor. And the predecessor would be an minus 1, right? Because that would be the n minus 1th term. Okay. And let's just write down what this looks like. So we've got a1, a2, and so on until we get to an minus 1, an plus 1, and we just keep going because it's an infinite sequence. So we see the predecessor of an would be an minus 1, the successor would be an plus 1. Okay. The next thing to say here, given any positive integer n, right? So by integer, I just mean a whole number. There is a corresponding. So by positive integer, that's the same thing as a whole number. So there's a corresponding number an. Right, so if we just pick a number, then we're going to get a corresponding entry in our sequence, right? So if we just pick the number, let's say 3, then we have a3 would be the third entry in our sequence, it's the third term. Okay, and I can say here, we can define a sequence as a function whose domain is the set of positive integers. Right, so what I mean by that is, well, let's say we have the input of, as I said, 3. So let's say 3 is our input, that's the positive integer that we're putting in. Then our output would be whatever the third entry is. And that's how we're defining our function. So let me write down our notation here. So we can denote a sequence sequence, let's say our sequence is A1, A2, and it just keeps going, right? So you just got infinitely many of these terms. We can denote it by, we'll say an. So this notation just means all of the numbers, right? So A1, A2, A3, and just all of the entries, right? So this is the collection of all of these. Or we can say, just be a bit more specific with it, this is the collection of ANs from n equals 1 to infinity, right? So this is just all entries AN, where n is ranging from 1 to infinity. This means the same thing. Another way we can define a sequence, like we can say or by a formula describing the nth term, right? So these are two ways of describing a sequence, and the third way is what I said here. A sequence can always be described as a function. The function doesn't necessarily have to be nice, right? We don't necessarily have a nice function that's the same for this and this and this, but we can say that it has some function. So let's just draw an example of what I'm talking about here. So an example is going to be, let's say we have the sequence. This was a poor drawing here. say we have a sequence, brackets, so this is 1/2, 2/3, 3/4, 4/5, dot dot dot. And you can think of what the general formula should be here, but remember, this was n equals 1. Let me use a different color here. This was n equals 1. This was n equals 2, n equals 3, n equals 4. So we can say that the numerator is the same thing as n, but the denominator is n, but you've added 1 to it, right? So this is n over n plus 1, and in general, our formula, as we just observed there, should be n over n plus 1, where here our numerator, or this is the nth term, right? So this is the first term, second term, third term, all the way up to this is the nth term, and of course this is an infinite sequence, because those are the only things that we're talking about in this section, right? So we can see here that this is our sequence, and we can describe it in two other ways, right? So I want to use this notation that we wrote up here. So I can say here, it can be described by, let's say here, I said we can just describe it by putting in these brackets our formula for an. So it can be described by n over n plus 1 inside of these brackets from n equals 1 to infinity, right? So that means the same thing. Writing out this list of numbers is the same thing as just writing this, because it's just understood that the way you get each entry is you take the entry and you plug it in for each, or you take the number of which term it is. So let's say you have the first term, you plug in 1 for n. So that would be 1 over 1 plus 1, and that's how you get the first term. And you just use this formula to find all the terms. So this means the same thing as this. And the other way of describing it, and by an equals n over n plus 1. Right, so I said we can alternatively just describe it using the formula for the nth term. So we can either describe it using this, or we can describe it using just this formula. They all mean the same thing. Okay, let's draw one more example here. Example, this, let's write this out. So this would be the square root of n minus 3. Sequence, sorry, struggling to draw these brackets today. From n equals 3 to infinity can be described by, so we said one way of describing it is just by using the formula. This is our formula. So we can just describe it by an equals square root of n minus 3. And notice, if we just left it here, if we just described it by this function, we're leaving out the fact that this actually starts at n equals 3, not n equals 1. So if we just draw the function, or if we just write the function without specifying, then we're assuming that it starts at n equals 1, but here this actually starts at n equals 3. So we need to specify this is for n greater than or equal to 3. So this is one way of describing our sequence. So the other way of describing our sequence is just what we did here, where we wrote out all the numbers. So if we just write out all the numbers, right, so it says here we start at n equals 3. So if we, let me just write here, so we're going to do n equals 3. Next we're going to do n equals 4, n equals 5, n equals 6, n equals 7, and n equals 8. So I'm just going to write out all of these terms here. So if we write this out, if n is equal to 3, then you're going to get the square root of 0 which is 0. If n is equal to 4, you get the square root of 1, which is 1. If n is equal to 5, you get root 2. If n is equal to 6, you plug it in here, you get root 3. If n is equal to 7, you plug that in here, square root of 4, that's 2. If n is equal to 8, you plug that in here, you get the square root of 5, and so on. Right? So we can either describe our sequence using this list of numbers, or we can use this formula, or we can write this notation. So all three of these things mean the same thing. Okay. So let's move on to, well, I would say our first example, but our first example that I'm going to put a number next to. So, example number 1, we're going to say find a formula for the general term an of the following sequences. Right, so they're just going to give you a list of sequences, and you've got to figure out what formula we're using. Right, there's not always going to be a nice formula like this, but you got to figure out. For these ones, there will be a nice formula, so we got to figure out what the formula is going to be. Okay, so let's say our first sequence is 1, 3, 5, 7, 9, and so on. So these questions are just all about figuring out what the pattern is, right? So let me write out here. A1, that's our first term, is 1. A2, our second term, is 3. A3, our third term, is 5. A4, our fourth term, is 7. And A5, our fifth term, is 9, right? So that's the information that they've given us. And we need to look at these numbers here, these subscripts. So this corresponds to which term it is, which entry, right? So this is the first term, second term, and so on. We need to look at how the subscripts relate to the actual numbers that are in the sequence, right? So you have to look at how do you get from 1 to 1, 2 to 3, 3 to 5, 4 to 7, and 5 to 9. So we've got to look at what our formula should actually be. Okay, so the question here, what do we do to each subscript, which is n, to get the corresponding term? Right. So we just got to look at the subscripts and see how they relate. So we can look at, well, what happens to get from here to here? So 4, that's kind of close. If you double it, that's going to give you 8. And 8 is kind of close to 7. If you take 3 and you double it, you get 6, which is kind of close to 5. If you take 2 and you double it, you get 4, which is kind of close to 3. So I encourage you to pause it here and think what the formula should be. But it turns out our formula, an, is going to be equal to, so you double the number and then you subtract 1. So it's going to be 2n minus 1, right? We can just check that that works for all of these. 2 times 1 minus 1, that's 1. 2 times 2 minus 1, that's 3. And that works for all of these. 2 times 5 minus 1, that gives you 9. Right, so that's our formula. So that's one way of describing our function. The way is by just describing the formula. Okay. So I'll say here, so the sequence of positive odd numbers can be written as, remember our other way of writing this was 2n minus 1 from n equals 1 to infinity. Right, so that's what we concluded here, right? Because this was the sequence of positive odd numbers, and we figured out our formula for each of these. Okay, so let's look at part B. That's part A. Part B is going to have the sequence 2, -4, 6, -8, 10, and -12. Okay, so again, we just look at what we have in each entry. So A1 is 2, A2 is -4, A3 is 6, and so on. Right? So we just need to look at what's happening to the values of n to get to the entries that we have in the sequence. So we need to figure out how to get alternating positive and negative signs. So we get alternating signs by multiplying by powers of -1, right? So if we just multiply our formula by some power of -1, then we're going to be able to get these alternating signs. So we need to figure out what the power should be. So that's going to be the next thing. And this type of pattern can come up in quite a few problems, so it's very helpful to know how to do this. Okay. So I'll write here, what should the power be? If the first term is positive. Okay. So let's say we have -1 to the power of n. Let's see what we're going to get if we have that. So let's think about if n is odd, then we're going to get a negative number, right? So we're going to get -1 if n is odd. And we're going to get +1 if n is even. Right, so let's look at the first term here. The first term is positive, and here, if we plug in n equals 1, the first term is actually negative. So if we use this formula, again, I need to use this color. If we use this formula, then the first term is negative. Right. Just noticing if we plug in an odd number, we're going to get -1. So the first term is negative. But let's instead look at what happens if we have -1 to the power of n minus 1. So if we have this formula instead, then if n is odd, if you plug in an odd number here, you're actually going to get, so odd number minus 1, that's even, so we're going to get +1 if n is odd, and -1 if n is even. Okay. So here are the first term. Right, so if n is equal to 1, then we get positive 1. So the first term is positive, right? So when deciding, whenever you have an alternating sequence like this, whenever you're alternating between plus and minus, you know you have to use one of these two, and we know by whether the first term is positive or negative which one we should pick. So here the first term was positive, so we need to pick the second one, negative 1 to the power of n minus 1. Okay. So that actually tells us what our answer should be. So an equals negative 1 to the n minus 1. So that's our alternating part. And then we need to look at what's happening to the actual numbers themselves, right? So this is n equals 1, it's getting doubled. This is n equals 2, it's getting doubled. This is n equals 3, it's getting doubled, right? So we should actually be writing here, this is this alternating part times 2n, right? Because for n equals, let's say you take the third term, n equals 3, this part is going to give you 6, and n equals 3, 3 minus 1 is an even number, so this part is going to be positive, so you get positive 6. So that's how you figure out what the formula should be there. Okay, and let's just go over one last part here to this problem, part C. Let's say you have the sequence 4 over 3, negative 5 over 9, 6 over 27, negative 7 over 81, and so on. So when you get something that looks kind of complicated like this, what you want to do is treat the numerator and denominator separately. So I'll say here we're going to do the numerator and denominator separately. Right, so we just care about each part separately. So the first numerator is, so if we look at it, our first numerator is 4, our second numerator is 5, our third numerator is 6, and so on. So what we're going to get, so we go to, so it's 4, 5, 6. You see each time is increasing by 1. So the numerator, pause here, think about what the formula should be for the numerator. But it looks like you're taking this number and you're adding a number to it. Same thing here. So the difference between this and this is 3, difference is 3, difference is 3, and so on. So the numerator is given by n plus 3, right? Because each time this is the first entry, you add 3 to that 1, you get 4, and so on. So that's how we figure out the numerator. So that's the equation. And the denominators are, so just take a look at the denominators, see what you can notice about them. You got 3, 9, 27, and so on. Those are powers of 3. So the denominators are powers of 3. Okay. And I'll say here the alternating signs and notice here the first sign is positive, so first sign is positive, means we multiply by, right, so you just look at what I said here. If the first term is positive, we multiply by this. Now, I'll say here, this negative 1 to the power of n minus 1 is actually the same thing as negative 1 to the power of n plus 1. right? So the reason for that is if n is an odd number, this power is odd. Or sorry, if n is an odd number, this power is even. This power is also even. If n is an even number, this power is odd, and this power is also odd, right? So if you ever see this, this means the same thing as negative 1 to the n plus 1, right? So we need to use this, but that's the same thing as this. So since we have the alternating signs, here we have the alternating signs, and the first sign is positive, so we need to use this, but it's the same thing. Okay, so now we can actually write our formula. So an equals, so we said we need to multiply by this negative 1 to the n plus 1. And our fraction should be, so we know the numerator was n plus 3. And the denominator is powers of 3. The first one is 3. So we're going to have 3 to the power of n. Right? So that's actually our formula. So negative 1 to this power times n plus 3 over 3 to the n. So that's our formula. Okay. The last thing I should note here, or I guess the next thing I should note here. Right, so that's the end of the example. But every sequence that we've analyzed so far by creating these formulas has actually had a nice formula that we could figure out for each of these, but that's not always true. So some sequences, I keep trying to use my red. So some sequences can be described by a simple equation. Right. So it's right here. Let's say we have the sequence 3, 1, 4, 1, 5, 9, and so on. So you might recognize that this sequence is actually, so where an is the nth digit of pi, right? So if we just write out the digits of pi, we don't have a nice formula to figure out the digits of pi, right? If we did, then that would actually be pretty nice, but we have to use supercomputers to figure out what the next number of pi should be, right? We already know quite a few places, but in order to figure out an extra place, it actually requires now quite a bit of computing power, right? We don't know all of the infinite places of the digits of pi. So we don't have a nice formula for that. So that's one example of a sequence. Another sequence is what we said earlier, the Fibonacci sequence. So it turns out, so let's say this is our sequence. So this was the Fibonacci sequence is defined recursively as f1 equals 1, f2 equals 1, and fn equals fn minus 1 plus fn minus 2, where n is greater than or equal to 3. Right? So you can see we don't have like one nice, so here we just had one nice formula for an, but here we have to do what's called this recursive definition, where we're defining each entry based on the previous two entries. So we don't have just this one nice formula like we did here. Okay, so we don't necessarily always have a nice formula. That's the point there. Okay. So the next thing, consider the sequence I probably should have used a new board for this, but that's fine. So consider the sequence n over n plus 1 . So consider this sequence from n equals 1 to infinity. So here, a1, so let's just work out what each term is going to be. So a1, the first term, is when you plug in n equals 1. So that's 1 over 1 plus 1, so that's 1 half. a2, we plug in 2, we're going to get 2 over 3. If we plug in 3, we're going to get 3 over 4, and so on. So if we plot this on a number line, so if we plot on a number line, then let's see what happens. So we've got our number line here, and let's say that this number here is 0, and this number here is 1. So we're just looking at the region between 0 and 1. And let's look at where each of these falls. So a1 is a half, so it's going to be halfway between here. So it's a1. a2 is 2/3, so it looks something like this. a2. a3 is 3/4, so it's around here. And then we get a4, a5, a6, a7, a8, and so on. And what happens is they just get closer and closer to 1, because let's say you think about, I don't know, 1,000, you're going to get 1,000 over 1,001, which is a very close number to 1. So you're just going to keep getting closer and closer to 1. So let me write down what I'm saying there. Okay. So we see that an gets closer and closer to 1 as n gets larger and larger. In fact, we can see algebraically that 1 minus what I said the formula should be here. So 1 minus what we wrote the formula as. So 1 minus n over n plus 1. So if you combine the two fractions, so this is n plus 1 over n plus 1 minus n over n plus 1, so you're going to get 1 over n plus 1. So if we do 1 minus this, we get that. And 1 over n plus 1 goes towards 0 as n goes towards infinity. Right, so this number here is going towards 0 as n is getting infinitely big. What does that mean? That means that our sequence is going towards 1. So writing in math, actually what I said there, 0 equals the limit as n goes to infinity of 1 minus n over n plus 1. So that's what I said there. And if you break that up, so 0 is limit as n goes to infinity of 1 minus limit, oh yeah, that is right. Okay. N goes to infinity of n over n plus 1. Right, so that's 1, that's that limit. So what we can do there is just add this limit to both sides, and we get that the limit as n goes to infinity of n over n plus 1 equals 1. Right. So we can actually look at these sequences and look at, well, are they actually approaching any numbers? So that's what we're going to be looking at now. So we can see this sequence is actually approaching the number 1. Right? We found that this limit is 1. Okay. So let's say here, intuitive definition, a sequence an has the limit L if we can make an as, so this is, sorry, an as close to L as we like by choosing n sufficiently large. Right? So if we want to say, well, I want this number to be within 0.1 of 1, then we can just make this subscript n really big, and then we can say, well, eventually you get to a term in the sequence, or point in the sequence, where all of the entries after that point in the sequence are actually going to be closer to 1 than 0.1 away from that, right? So I'm just saying what I said here. So a sequence an has the limit L if you can just make the entries as close to L as you like just by making n to be really big, meaning so n was the term in the sequence, so just by picking really far out in the sequence. Okay, but let's write this a bit more rigorously. So let me write that on another board. So that's just kind of the intuitive way of writing it, but let me actually write this down a little bit more rigorously. Okay. So we say the limit as n goes to infinity of an equals L, or an goes to L as n goes to infinity. So that's the same thing as what we said there. If limit as n goes to infinity of an exists, meaning it exists and it's not infinity, we say the sequence converges otherwise we say it diverges. Right. So similar to when we were saying that integrals either converge or diverge, then we're going to say that a sequence converges if this limit of whatever this formula was, or this limit of the entries, right? So if you take the limit as n goes to infinity of these entries, then if it goes towards this number L, then we'd say it's convergent, and if it goes towards, if it just doesn't go to a number, or if it goes towards infinity, then we'd say that it's divergent. Okay. So say IE is convergent / divergent. Okay. Now, I'll say here something to note is that divergent sequences don't all diverge in the same way. Okay. Right, because let's say something just keeps alternating between two numbers, then we'd say that's divergent because it doesn't actually have a limit. Or if it just goes to infinity, we'd also say it's divergent. Or if it just doesn't go to anything, like if you have the digits of pi, well, that's divergent because it just doesn't go to any number, right? We can't just say that these numbers are approaching some number. It just doesn't go to anything. So let's write here the limit as n goes to infinity of an equals infinity if for any integer m there is a number n there is an integer big N such that if you choose your little n to be bigger than this number big N, then your an is guaranteed to be bigger than big N, right? So we're saying it's divergent if you can just pick any number you want and say, well, all the numbers, all the entries in the sequence after some point, so after this point, all the entries in the sequence are going to be bigger than m. And you can do that for any possible number, right? So if you wanted m to be 10, then you can pick a point in the sequence where all the numbers after that are bigger than 10. If m you wanted to say is a billion, you can say, well, there's a point in the sequence such that any number after that is a billion, at least a billion, bigger than a billion. Then, if that's true, then you'd say that the limit goes towards infinity, right? Because it just keeps getting bigger and bigger. So we'd say that this limit is going to be equal to infinity. And I'll say here, if the limit as n goes to infinity of an equals infinity, then we say that an diverges to infinity, right? Because we said it's divergent, and we'll just say that it diverges to infinity. Okay, so let's write down a theorem. So theorem if limit as x goes to infinity of f of x equals L and f of n equals your entry an, when n is an integer, then the limit as n goes to infinity of your entries an in your sequence is going to be equal to L. Right? So if you've got your function that you're describing your sequence by, then you can just take your limit of your function, and if that's equal to some number, then you'd say that your sequence also converges to that number. Right? So that's just kind of a helpful tool in order to tell when our sequence is converging. So example number 2 is going to say determine if an equals e to the 2n over n converges or diverges. Okay. So as I said here, what we do here is just replace the n's with x's and then just take our limit like we would normally do in Calc 1. So if we let f of x equals, so we just replace the n's with the x's, so e to the 2x over x, then f of n equals an for all integers n, right? So that's just what we said here in the theorem that we needed. So now we can just take the limit of this function. So the limit as n goes to infinity of our entries an, that's what we're interested in finding to see whether our sequence is convergent or divergent. We said we replace that with the x's. So the limit as x goes to infinity of e to the 2x over x, and now we can just solve our limit normally. So whenever we get stuck trying to solve a limit, first thing is we just try plugging in the values. So if we plug in infinity, we're going to get e to the infinity over infinity, which is infinity over infinity. And if you remember, what we can do whenever we have 0 over 0 or infinity over infinity is that we can use L'Hopital's rule. So whenever we have that, we can use L'Hopital's rule. Right? And all that rule is saying is this limit is equal to the limit as n goes to infinity of the derivative of e to the 2x over the derivative of x. Right? So now we just got to take our derivatives. So this is the limit. That's my cat. That's the limit as n goes to infinity of, so now the derivative of e to the 2x, we've got to use the chain rule. So we take the derivative of e to the, just e to something, that's just the same thing. So the derivative of the outside function e to the x is e to the x. So we take the derivative, we plug back in the inside function, and now we multiply by the derivative of our inside function. And in the denominator here, the derivative of x is just 1. Okay, so let me just go ahead and erase this part. Right, so the derivative of 2x is 2. So it's the limit, oh shoot, sorry. I just subconsciously replaced these with n's. These are supposed to be x's, because here you've got x's. Those are supposed to be x's. But you got the limit as x goes to infinity of, this is 2 e to the 2x. And now if x is going towards infinity, what is this doing? It's going towards infinity. So this is infinity. And right, the other way of seeing that is just, well, e to some power that's going to grow much faster than just n, right? So this is going to be infinity. Okay. So whenever this limit is infinity, that means that our sequence is going to diverge. So this means that it diverges. So our sequence an diverges to infinity. Okay. Why did I write this here? Okay, well, just a bit of a note in case you encounter this type of sequence. Okay, this is just a bit of an aside. So we've already finished the problem here, but recall from Calc 1. Now I remember why I wrote this. So we're going to use this in an upcoming example, but here if we have the limit as x goes to infinity of 1 over x to the power of r, then this is going to be equal to 0 when r is positive, so r is greater than 0. Therefore, let's say we have a sequence of 1 over n to the power of r, and we can ask what this is going to go to. Well, we said as n gets bigger and bigger, then this is going to go towards 0, right? Just because the limit of this function, if you replace the n's with x's, is going to be 0, so this sequence is going to go towards 0 as n goes to infinity, and when r is greater than 0, right? Still you need that r is greater than 0, but as long as r is a positive number, then this sequence is going to go towards 0. So we're going to use this in a little bit. But first, I want to write down this note here. So limits of sequences follow the same rules as limits of functions from Calc 1. Right, so the first rule I'll write down here is if we have the limit as n goes to infinity of the entry of one sequence an plus or minus the entry of another sequence bn, then we're going to get the limit, we can just break it up. So we get the limit as n goes to infinity of an plus or minus the limit as n goes to infinity of bn. Okay, let's say for number 2, if we have the limit as n goes to infinity of an times bn, then this is going to be equal to, as you can guess, the limit as n goes to infinity of an times the limit as n goes to infinity of bn, right? So you can just break it up like that. And the last thing that I'm going to write here, part 3, is going to be if you have the limit as n goes to infinity of the entries of one sequence A over the entries of a second sequence B, then again you can just break this up. So this is going to be the limit as n goes to infinity of an over the limit as n goes to infinity of bn. Okay. And I'll write here, we were only able to do this in Calc 1 if the limit as n goes to infinity of bn is not equal to 0. So you just have to be careful there that you can only use that property if the bottom limit is not 0. Okay. So now we want to use all these things to actually solve a problem. So I think I misnumbered this, but this is example 3. So example 3. So find the limit as n goes to infinity of the sequence 3n squared minus 1 over 10n plus 5n squared. Okay, so we've got to figure out how we're going to solve a problem like this. This is supposed to be 5n squared. It's a little bit hard to read. Okay, so our method. Our method is whenever we try to take a limit of a fraction like this, we're always going to be dividing by the highest power of n in the denominator. So divide the numerator and denominator by the highest power of n in the denominator. And in this case, we're going to divide by the highest power in the denominator, which is n squared. Okay. So that's what we need to do. So remember in Calc 1, that's the same thing that we did. So what we take is the numerator, we divide by the n squared, and we take the denominator, and we divide by, again, n squared. Okay, so I just kind of write the parentheses to help us keep track that these two are smaller fractions inside of the bigger fraction. Okay, and now if we do our division, this is 3n squared divided by n squared, that's 3, minus 1 over n squared, over, this is going to be 10 over n plus 5. Okay, so we can write here, so, I mean, what we did in the last part was replace all the n's with x's, but we don't need to do that if we don't want to. So we'll just write here the limit as n goes to infinity of, the limit as n goes to infinity of the sequence 3n squared minus 1 over 10n plus 5n squared. Right, so remember this is a sequence. This isn't just some limit. This is the limit of the sequence of numbers. But we can just solve it the same way. Right, so what I did in that other theorem is just say we're just taking the limit of this function. So if we take the limit of this function, same thing as the limit as n goes to infinity of 3 minus 1 over n squared over 10 over n plus 5. Okay. And we use what I wrote here. So that's the reason I wrote this here. We've got 1 over x to the r. That's always going to go to 0 as long as r is positive. So here we've got this 1 over n squared. We said there that that has to go to 0. And here we have this 10 over n, which we said also has to go to 0. Because n is getting infinitely big, so these denominators are getting infinitely big, so the fractions go to 0. So this goes away, and this also goes away. So if those both go away, then you're just left with 3 over 5. Right, so what we can say is, so the sequence converges, and its limit is 3 over 5. Right, so what all that means is as you get bigger and bigger entries in the sequence, or sorry, what I meant to say is as you go further to the right in the sequence, as you get bigger, or as you get higher number terms, right, so as you get to the 1000th term, the millionth term, and so on, all those terms, all the entries are actually going to get closer and closer to 3 over 5. Okay. But what I'll say here is we can't always just take the limit of our sequences especially if they alternate. So we'll use this theorem. We'll use this theorem. Okay, so theorem number 2. Number 2 is going to say the limit if the limit as n goes to infinity of the absolute value of an is equal to 0, then the limit as n goes to infinity of an equals 0. So if our sequence alternates, we can't just take its limit. That's when we have to be a little bit more careful. But if we take the absolute value of the alternating sequence, then it's just going to be just a normal sequence. Because if it's just alternating between a plus and a minus, we can get rid of that when we take its absolute value. If this limit is going towards 0, then we didn't actually meet the absolute value symbols. Then the limit of the sequence is actually going to 0. To show you what this means in a graph, let's say that these are our entries in the sequence. Let's say this is our first entry, this is our second entry, third entry, fourth entry, fifth entry, sixth entry. And you can see that they're just getting closer and closer to 0, then it doesn't really matter that they're alternating because eventually they're just all going to 0. So we just take its absolute value, take the limit of the sequence, it's going towards 0. So that's what this theorem is saying. This is an important tool. Okay. So let's write down the next example. Okay. Example number 4 is going to say evaluate the limit as n goes to infinity of -1 to the n over n if it exists. Right. Okay. So notably, we can't just always take the limit, right? Because if we had something like the limit as n goes to infinity of -1 to the n, then what's happening here is your first term is 1, sorry, what I meant to say. Your first term is -1, second term is 1, third term is -1, fourth term is 1, and so on. So if you look at a graph of what's happening, you're just alternating between values like this. And what's happening, limit as n goes to infinity is the horizontal asymptote. You can ask the question, do you have a horizontal asymptote here? And you definitely don't, right? So here, this does not exist. This does not exist. So that's a problem. And the way we deal with these alternating things is by using the theorem. So we need to try to take the limit of the absolute value. And if it goes to 0, then we're good. Okay. So the limit as n goes to infinity of the absolute value is what we're going to try to take. So if we take the absolute value of this thing, then the alternating part goes away. So we've got the limit as n goes to infinity of 1 over n. And remember what we said, if the denominator is getting infinitely big, then this is going to 0. So, by theorem 2, we can say that the limit as n goes to infinity of our sequence with these entries is going to be equal to 0. Okay, so let's talk about another theorem. This is theorem 3. If the limit as n goes to infinity of an equals L and the function f is continuous at L, then the limit as n goes to infinity of f of an equals f of L. Right, so all this is saying is if we've got this function, we can move this limit sign on the inside as long as this function is continuous at L. So as long as this function f is continuous at L. So using this, let me erase this next board. I want to use this to solve another example. Okay, so this one looks a little bit more complicated. So number 5, evaluate the limit as n goes to infinity of sine of pi over n. And what we said here is if this limit on the inside is equal to some number and the function is continuous at that number, then we can just move this limit into the inside. So what I can write here is since f of x equals sine x is continuous everywhere, the limit as n goes to infinity of our sine of pi over n is going to be equal to, if I just pull the limit on the inside, so it's going to be sine of the limit as n goes to infinity of pi over n. Okay. So now we can actually just take the limit of the inside, and notice pi over n, we can just factor out a pi. So this is sine of pi times the limit as n goes to infinity of 1 over n. Okay, but what did we say this limit on the inside was? We said this was 0, right? So this is going to be sine of pi times 0, which is the sine of 0. And if you remember our graph of sine of x, it looks something like this. And if you take the sine of 0, it's going to be 0. So that's 0. Okay. So that's our answer here. Our limit is 0. Okay. So the last part of this section, let me write it over here. Let me just erase this. The last part of this section is talking about, I want to erase this, is talking about monotonic and bounded sequences. Okay. So, definition, a sequence AN is called strictly increasing, So we'll say it's strictly increasing. We don't need the word strictly, but if we say a function is increasing, that means it's strictly increasing. So if AN is strictly less than AN plus 1 for all n greater than or equal to 1. Which is the same thing as saying, so aka A1 strictly less than A2, strictly less than A3. So here similarly we've got AN minus 1 is strictly less than AN is strictly less than AN plus 1, and so on. Right? So here, AN is strictly less than AN plus 1 for each of these entries. So this is the pattern that you get. So what this means is you just have a sequence that looks like maybe 1, 5, 6, 9, 9.1, 9.6, 12, and so on, where just each entry just keeps getting bigger, right? So this is called an increasing sequence. And strictly decreasing if AN is greater than AN plus 1 for all n greater than or equal to 1, right? So again, that would just look like a list of numbers that just keeps going down. Okay. Sequences that are increasing or decreasing are called monotonic. Right? Monotonic just means it's moving in one direction. So if it's increasing or if it's decreasing, then it's moving in one direction, so we call it monotonic. Okay, so example number 6. Show that the sequence AN equals n over n squared plus 1 is decreasing. Okay, so we want to show right, so remember if it's decreasing, AN is greater than AN plus 1. So we want to show AN is greater than AN plus 1, aka, so let's just write down what that means. So AN is what I wrote up here. So n over n squared plus 1 is greater than, and here, AN plus 1, that just means wherever I see an n here, I need to replace it with an n plus 1. So if I do that, then we're going to have n plus 1 over n plus 1 squared plus 1. So I just replace these n's with n plus 1. Okay. So if this is true, then it turns out that our function is decreasing. Okay. So in order to try to figure out what this means, I'm going to go ahead and cross multiply just to get rid of these fractions. So I'll say here, we cross multiply, and I'll say here, remember n is greater than or equal to 1, right, because you can't have a term before the first term. So we're not going to use this fact until a little bit later, but we need to remember this, so we just cross multiply to get rid of the fractions. So I multiply both sides by this denominator, so on the left we're going to have n times this n plus 1 squared plus 1. And on the right side, I multiply both sides by this denominator, so we're going to have n plus 1 times n squared plus 1. Okay, so we're trying to prove that this is true, so we just need to expand everything. So we're going to have n times, this would be n squared plus 2n plus 1 plus 1 is greater than, and then on this side, we just need to FOIL this out. So we're going to get n cubed plus n squared plus 1. Okay. And now we can just multiply what this gives us. So we're going to get n cubed plus 2n squared plus 2n is greater than, on the right side we have n cubed plus n squared plus n plus 1. Okay? And what we can now do is just go ahead and, what did I do here? Yeah, so let's just get all the n's on the left side. So let's just move everything with n over to the left side. So if we do that, so I'll do minus n cubed minus n cubed. Anything you do on the left, you also have to do on the right. I'm going to do minus n squared minus n squared minus n minus n. So if we do that, what we're going to get is going to be n squared plus n is greater than 1. So we're trying to figure out whether this is true. But remember here that n is greater than or equal to 1. So if we add these two things together, since n is bigger than or equal to 1, then this should actually be true. So since n squared plus n is greater than 1 for all n greater than or equal to 1, the sequence is decreasing. Okay. And now let's just write down one more definition. So this is something you'll see in the homework. So definition, a sequence is bounded above if there exists a number m such that an is less than or equal to capital M for all n greater than or equal to 1. So that's kind of what you would expect it to mean, right? We say a sequence is bounded above by, let's say we say a sequence is bounded above by 10, then each entry in the sequence is less than 10, right? So that just means if I have a sequence of numbers and I say it's bounded above by 10, then every single entry in that sequence is less than 10. Okay. And I'll say it's bounded below if there exists a number m such that m is less than or equal to an for all n greater than or equal to 1. Okay. So that's kind of also what you would expect. I'll say a number is, I'll say a sequence is bounded below by, let's say, I don't know, 3, if every entry in the sequence is bigger than 3, right? Okay, and I'll say, okay, next thing I'll say here is a sequence is bounded, a sequence that is, that's what I meant to say, a sequence that is bounded above or below is called a bounded, that's, I messed up writing that, bounded, that's right, I messed up this word here. That's supposed to be and. It's very important. It's supposed to be and. So a sequence that is bounded above and below is called a bounded sequence. Right? So it's very important. The sequence is both bounded above and bounded below, so you can say that every number in the sequence is between two numbers. So if it's a bounded sequence, every number in the sequence is both greater than some number and it's less than some other number. Okay, so the reason why this is important is theorem 4. So this is the last thing, so theorem 4. Okay, so every bounded monotonic sequence, remember, monotonic just means it's either increasing or it's decreasing. So every bounded monotonic sequence is convergent. More specifically, so we'll say here if an is increasing and bounded above, then it converges. And second thing here, if an is decreasing and bounded below, then it converges.